Hello, everyone. Welcome to the second part of the Richardson RFPD Tech Chat about fast switching with wide bandgap transistors. My name is Sefan Witte. I'm Senior Business Development Manager for Power Products in Europe at Richardson RFPD. Today, I have Steve Roberts with us. He is Innovation Manager at RECOM Power with experience of more than 20 years in power conversion. Thanks, Steve, to join us today for the second session.
Thank you for inviting me.
So, Steve, today we want to talk about how to ensure the reliable, fast switching of wide bandgap transistors in high power application. So, Steve, can you tell us something about the challenges we are facing in such switching designs, and especially in high power designs here?
Yes, last time we talked about the problems of switching at high frequency, and I'm going to try and talk to you today about how you can actually solve some of those problems. I've got a presentation I want to show you. So this one's called "With Great Power Comes Great Responsibility," because essentially that's the problem when you're switching high power at fast speeds. So you need a gate driver that can charge and discharge the gate capacitance of the transistor very quickly. And this is a typical gate driver circuit you might see with separate on and off resistors, so you can control the speed of switching on and off. And quite often these gate drivers are specified with like 2 amps or 4 amps drive current, but the actual power they need is surprisingly small because the switching time is such a short period of time. So if you look at the equation there, you can see that for 50 kilohertz switching, which is not particularly fast, I know, you only need 1/3 of a watt of power. So it's really low power for the gate driver, although it's high current. And traditionally, if you look at the gate driver data sheets, they just assume that a isolated power supply is available, and they just say, connect here to an isolated power supply, and assume that it's there, and it's often the power supply itself, the isolated power supply, is as important as the actual gate driver specifications themselves. And traditionally, so these are the two kind of what I call skyhooks. They're invented links to where they don't go anywhere. They just say on the data sheet, oh, just connect a power supply to these points. And they don't say where that power is coming from. And traditionally, it's done through a bootstrap. So you have this classical bootstrap gate driver circuit where you have a diode on the top here and a resistor and a capacitor, and while the switching node is switching up and down at this point here, this capacitor takes some of that voltage and kind of bootstraps its own power supply, which is fine with a lower frequency. But when you get to higher frequency, there's a lot of problems with this kind of design because it's not very stable, especially during the first few pulses. And wide bandgap transistors can switch so fast that even the first pulse or the second pulse, if it's not stable, it can cause you serious problems. So here you can see a circuit which is based on this design, and this is I used this from a TI data sheet, and you can see here these ringing and output variations in the voltage, and that's caused by the fact that you're switching at such high frequencies, and the parasitics start to affect the voltage because the diode reverse recovery time is too slow, or has and these variations can easily destroy the gate driver.
Mm. Yeah, very interesting. Yeah, Steve, to establish second source transistors will be more and more important because of the long lead times and all this challenges in the supply chain. So what are the challenges to use different SiC transistors from different vendors?
Yeah. The problem here, as you see here, is that the headroom between the recommended voltage range of the gate drive, and the maximum voltage is very limited. The old IGBT, you can see here, it was traditionally -9 to +15 drive, and it usually takes +20 to -20 without any problems. But if you try to switch that with a silicon carbide, you'll find that you may have serious problems because they're designed in different ways and the limits are different. So typically a silicon carbide will only take -10 as the absolute maximum. And sometimes the maximum positive voltages are different depending on different vendors. So that creates problems. You can't just switch from one vendor to the next with an existing design and expect it to work properly. You might find that you just put a different transistor in and that doesn't work anymore because you're driving it too hard with too high a voltage. On the other hand, if you don't drive it fully, you're going to have problems with efficiency. So you've got a difficult problem here, and GaN is especially sensitive. Between the recommended drive voltage, which is 6 volts, and the absolute maximum, which is 7 volts, there's only 1 volt difference. So that makes it extremely difficult.
Yeah, I see. So this is really a challenge to switch between different vendors. So I see here that there is the negative voltage of -5 volt or -4 volt. Yeah. Well, what is the reason that there is the negative voltage is used?
Yeah, this is because you want to switch off properly. The transistor will switch off with 0 volts. But you've got these inductive elements that are part of the gate inductance and the layout inductance on the source side and the drain side, and these inductances, when you're switching very quickly, they'll generate a voltage across them. So what happens is you especially when you switch the transistor off, you get a very high change in the voltage at dVdt. And that flows through the transient capacitances, and it raises the gate voltage back up again. So in the worst case, you can get this bump in the actual gate drive. The transistor can switch itself back on again by itself. So in order to stop that, you drive it with a negative voltage, and that means you guarantee that when you turn the transistor off, it stays off, even if the layout inductances try to generate a voltage to turn it back on again.
Okay. So for there are some more challenges, I think, especially also in the layout and what you have really take care for, yeah, because of the high switching frequency you have there in the system.
If you're switching like 1,000 amps per microsecond, which is entirely possible with these kind of power levels, even a 5 nanohenry inductance will generate 5 volts. So across it. So, and 5 nanohenries is a 5 millimeter length of PCB track. That's how sensitive the layout is. So the way to solve that problem is to generate, say, the negative voltage, and this way you need a DC-DC converter. So you can't generate a negative voltage using the traditional bootstrap circuit. So you need to add an extra isolated power supply, and then you can choose the correct high voltage, the positive voltage, so you get the maximum enhancement of the transistor. But you can also choose the negative voltage, so you turn the transistor off properly, and these voltages are stable. That means that they're stable even before the transistor starts switching. So that means that even with the very first pulse, you get a stable switching. And the other problem we have with modern designs is that the power ground are not always the same. So the main power ground and the power ground for each leg of a half bridge or full bridge converter may not be exactly the same. All of these layouts, inductances in the way, and that means that you can solve all of these problems simply by having DC-DC converters on both the high side and the low side, which is a bit unusual, I know. But if you have a low side DC-DC converter, that means that you can float the ground to the ground of the transistor, which means that you ignore all of the layout inductances. They don't affect the switching characteristics at all. So for a very high-speed switching design, it's best to use isolated power supplies on every single driver, even if it is close to zero on another design. So finally, to conclude, if you want to do this high-speed switching, if you have isolated DC-DCs, you can get much tighter tolerances. Use both the DC-DCs on both the high side and the low side legs to avoid any problems with layout parasitics. And it also allows you to choose different drive voltages according to different vendors and to different types of transistor.
Okay, yeah, thank you very much, Steve. Very interesting. And I'm looking I'm very appreciated to have you here and looking forward to have you in another chat later on in the future. Thank you very much and bye for now.
Bye-bye.